So today we've got 4 speakers. They'll be speaking on different topics regarding the future of CHP. And our first speaker today is Mr. Doug Cash. He is with the On-Site Energy Group at DTE Energy Services. He's been there 12 years. He's a business grad. Now, I asked him what his alma mater was so I could brag for him, and he said Michigan State and U of M. So I'll introduce him as a U of M grad. Go Blue. And today he is going to be speaking to us on a presentation titled 3 Case Studies of CHP Project Implementation Using a Third-Party Structure. So please help me welcome Doug Cash.
Thank you, Sam. So just to introduce myself in DTE, maybe for those of you who aren't familiar, within the state of Michigan, many people know us as their electric or gas utility. The DTE Electric is the former Detroit Edison, and DTE Gas was formerly known as Michicon. So that's how most of the people in Michigan know us. However, I work in the DTE Power and Industrial Group, which includes about 70 projects across the country, including a number of CHP projects. Now, I don't want to go into too much detail about the benefits of CHP. I'm sure some of my colleagues here will share those as well. But I will say that there are a number of things that what we find is our industrial partners, our commercial partners, they don't have trouble understanding the efficiency gains or the cost gains associated with that efficiency, or even the reliability gains. But they do have trouble sometimes unlocking those gains in a capital-constrained environment. If it's an industrial, maybe they want to put their money to work on their core business rather than their utility infrastructure. So what we propose is a third-party ownership solution. So we help with the capability, the investments, the personnel, the expertise that allows them to unlock those benefits of CHP. Now we do that utilizing the business model acronym DBOOM. So BOOM, never a very good thing to think about in terms of power plants, but the DBOOM business model captures the design, build portion of the project, the ownership, including the owner's risk during the term of operations, and the operations and maintenance piece. So most of our projects are structured around this DBOOM structure in some combination. From a DTE P&I perspective, as a third party, I would say the only combination that we don't typically engage in are just the design, build, and transfer. We typically like to have a long-term interest in operating and maintaining the facilities. It's a flexible structure as well, and so I'm going to go through a few examples that will show that one size does not fit all, but that the DBOOM structure allows us to bring value, to unlock that value of CHP for our hosts in a number of different situations. So these are the DTE Calvert City facility, DTE Marietta facility, and DTE Dearborn facility. So the first one is interesting. DTE Calvert City was actually built by Air Products. There was a coal plant that was being retired, and they saw the value in self-generating electricity. It went COD in 2000, and DTE became the owner-operator of that facility in 2011. So what happened, well, I'll mention a couple highlights maybe about that plant from a implementation and a history perspective. But Calvert City has the ability to go island mode. We have backup power from TVA, but we're able to serve the entire chemical campus in the event of a TVA outage. It has a dual HRSG design, which is somewhat unique. We don't see that all the time, but the exhaust heat off of the turbine feeds 2 trains of HRSG. Steam is very important to our customers, and reliability of steam is very important. So each train can operate independently or at the same time. And the export to TVA. That's something that not all industrials or commercial hosts are necessarily comfortable with, the power market aspect of owning or operating a cogen facility. So how does DTE Calvert City fit in with our DeBoom business model? So obviously from the start, it doesn't fit in with the design or build aspect of it at all. We bought this facility from an industrial. However, what's interesting about it is that industrial over time had sold off a number of their business lines on this chemical campus and had found themselves in the business of not just providing their own utility services, but providing utility services to a number of third parties. So our ownership capability allowed us to come in and help them get out of the business of being a utility service provider to third parties and allow them to focus on just the chemical business that they were in at that site. Since we took ownership, Air Products has actually left that site. So by divesting the operations associated with the utility services, they were also able to then sell off their chemical business in a much more straightforward fashion. From an O&M and ownership perspective, it's very much like any site we would have built. So we have owner's risk associated with the continued operations of that facility. The challenges are the challenges that come with serving a campus with customers with different schedules and different needs and different tolerances for outages at different times. So that's become a skill that we've had to develop over time, but it's one that we've brought to other facilities as well, is maintaining a continuous supply and coordinating all the needs of the different campus partners. As Sam mentioned, these slides are going to be available online. I know there's a lot of information about each of these projects. I just want to maybe highlight a couple of points. The second example is the DTE Marietta site. This is one where Solvay, our industrial host, lost their steam supply. They were on a district steam system and had been getting by with packaged boilers on a rental basis until they had figured out a long-term solution. The DTE was chosen through a RFP process which included an indicative design. So we competed with others on a planned facility, and we laid out commercial terms for how we would construct and own that plant once we were at COD. The facility itself changed tremendously during the development. So I think what's interesting about the design build is that we can come to a commercial agreement for how we will recover our capital, who will be responsible for what risks during the construction phase and during the term, but still remain flexible enough to accommodate those changes, to make sure that we build the right facility for our hosts. The site actually changed multiple times during the development, and we ended up building much further from the plant than we had ever anticipated. In terms of ownership and O&M, we have talked a lot about the ability to expand our facility now that we are up and running, and we're working on that currently. The third example, and this is one of the most recent, is the Ford Dearborn CEP. Ford is in the process of revitalizing their R&D facilities, and they've embarked on a 10-year process for doing that. They worked with DTE Energy Services on a central energy plant to serve the future needs of this campus. Now, DTE Energy Services brought in the local utility, which happens to be an affiliate, but I would say that the way we're working with our affiliate applies in other markets as well, and we have embarked on this process in other areas with other utilities. So this project is under construction. when it's completed, the generation assets will be owned by DTE Electric, our regulated utility affiliate. And DTE Energy Services will be responsible for the construction of the facility and the ongoing operations and maintenance of the facility. Our COD is targeted for the end of this year. We're very excited about this plant. This plant, if you think about the different constituents, it was a win for the utility because they were able to keep a large customer as a rate base customer. So Ford will continue to buy their power from DTE Electric as if this CHP was not there. The utility also, by making this investment in the CHP, utilized our skill set managing a smaller construction project. So this isn't a utility scale operation. And so P&I, by taking on the design build portion of it, can do that more efficiently. Ford, the benefit to Ford is their co-generated steam. So they get the benefit of the efficiency associated with CHP by paying a steam price, which benefits from the the CHP unit. They also reduced capital as DTE Electric is making the investment in the CHP portion of the facility. And they have the benefit of on-site generation. Now, while the CHP is not dedicated to this facility, if there were to be grid issues, the likelihood that this CHP would continue to be able to supply Ford is very high. P&I, DTE P&I benefited from this by utilizing all portions of the design, build, own, operate, maintain skill set. Maybe I'm getting ahead of myself with the operate and maintain since we haven't quite reached COD, but we're able to bring our skill set related to the construction, the design, and the ownership piece. So these are 3 examples that help us bring the benefits of CHP through a third-party structure. And while a number of the benefits up there pertain whether or not you're using a third-party structure, such as efficiency, the one that we focus on the most is the bottom one, that we allow our customers to focus on their core business while we take on the challenge associated with unlocking those benefits of CHP. Are there questions about these projects? Yeah. No, absolutely. The thermal load is very important to getting the benefit out of the CHP. So in that case, Air Products sold the production line that they were operating, so the thermal load actually stayed there. But we have had to focus on each customer individually, whether or not each of their businesses are sound, and have to run all the scenarios associated with who could leave this site or stop production, and would we still have enough steam load to produce to run the cogen efficiently. So the EES Coke battery is still operating in Detroit. We acquired a Coke battery in Pittsburgh that's no longer operating, but the EES Coke battery is still going strong.
All right, that's good to hear.
Yeah, great. Well, thank you very much.
Thank you. Next up, we have a paper titled Eastern Michigan University Recent CHP Upgrade Case Study. It's going to be presented by Jack McCormick, who is a mechanical engineer and project manager with Commonwealth Associates. He has a BS in mechanical engineering from Western Michigan University. He's licensed in several states throughout the country. He also is an active member of ASME B31.1 Power Piping Design Subgroup. And he has over a decade of experience in planning, design, construction, and commissioning projects. Please help me welcome Jack McCormick.
Good morning. Thanks for coming. I think I'm in Eastern time, so I think it's afternoon for me, but I'm still trying to catch up. Excellent. Okay. So this is a case study on the CHP project that went recently commercial operation in 2018. Hoping to get through today a quick introduction and talk about who Eastern Michigan University is, talk about the project and the goals and the outcome, and have time for questions as well. At least that's the plan. Players in this game were the owner is Eastern Michigan University. I'll talk a little bit more about who they are. NG as the EPC contractor, and then Commonwealth as the owner's engineer. We kind of walk through the steps with EMU during design and construction and commissioning. So Eastern Michigan University is a university in Ypsilanti, Michigan, just outside of Ann Arbor. It's kind of cool. It's in our backyard. Commonwealth Associates is in Jackson, Michigan, so there's only about 45 minutes from our corporate office. Made it pretty easy to help the owner during an owner's engineer during construction primarily. They started off with just over 100 students and has grown the campus to over 20,000, numerous colleges. And the part that's relevant to CHP here is the 120 buildings and 800 acres of space that they are providing electricity and steam to. Kind of a backstory on the project is Eastern Michigan University had a solar turbine. It was the Taurus 60. It was kind of an aging machine that took an unexpected outage, and instead of fixing that machine, they elected to replace it with a slightly larger machine. By doing so, they could buy less electricity from the utility, save some money in the dollar savings. Being a campus, like many operations, it needed to run. Construction had to happen with other parts of the energy center kind of in operation. They're looking at island in operation. They don't currently island. I'll talk a little bit about what they do, but they wanted the opportunity to do so, black start capability, and then do this under kind of a firm contract, which is why they went the EPC route. So to kind of give you a backstory on their energy portfolio, boilers in 1951, they added the CHP that I spoke of, the Taurus 60, in 87. I think it was 2016 or so is when we took that outage. And at that time, they had to decide whether or not they wanted to make that repair or replace their turbine with a larger one. So like most projects, you have to go through kind of a development study in the sense of understanding what the loads are on the campus, both in steam and electric. The electric is pretty straightforward, but steam is used for a lot of things there at EMU. They use it for domestic hot water heating, space heating, and some cleaning applications. So they use a lot of steam. They needed the flexibility. I'll talk about that. I'll have a slide on what their load profiles look like and how you have to consider matching equipment, both the CT, the HRSG, and in EMU's case, also duct firing for additional steam. Considering redundancy, and then just the operational issues that come with CTs, temperature, humidity, and elevation. And then the import requirements. So EMU operates in a way that they don't want to export. It's not their plan. It's not how they like to operate. They also like the security of having the utility connected in case they ever lost their CHP. So they maintain a load profile where they're always importing some electricity and staying synced with the grid. And so that was important in understanding what your true load is, whether it's if you have to operate the CT at certain loads, and also knowing that you need to import, considering that in the sizing of that equipment. We're looking at roughly $40,000 to $50,000 per savings to go with the newer, bigger machine. That's offsetting the electrical cost that they wouldn't have to purchase, and then of course minimal impacts to the campus. Ultimately, this contract was developed under a guaranteed savings terms. So the tricky part of the contract was understanding what part of the, auxiliary loads were associated with this new project. So dividing that up in the contract was a little bit messy, but for this project, ultimately it was the gross power of the CT less the fuel gas compression power. The other aux loads like boiler, feed water pumps and such were not considered in the guaranteed savings terms. Another kind of interesting point of that is the contract parameters for what was being used for the cost of electricity and then the cost of gas. The way this particular contract was set up is increasing over the contract terms for electric and then constant gas. It was a 3-year term, so using a constant gas, ultimately folks were comfortable with that. Okay, so the load profile, the orange is kind of the thermal requirements, the red is electrical requirements. This is a year-long graph here. So we can see the load profiles on a daily basis hopping all over the place. In addition, the thermal load kind of goes up as we get into the winter and then tapers back off for the summer. And electric load profile kind of doing the opposite. So in selecting the equipment, it's important to pick equipment that can meet all of those load profiles while also considering importing electricity so that they can stay synced with the grid. Another key component to this this upgrade was the controls integration. This facility that Eastern Michigan has, it's a building that has boilers in it and this aged solar Taurus 60 and HRSG. So over the course of the design and construction and ultimately commissioning and startup of it, at that whole time, the boilers had to stay operating, providing steam to the campus, and they had to purchase electricity from DTE. So during that whole process, it was important to understand where we could take outages, when those outages could, had to occur, and also keep everything online so they can continue to provide the steam and electricity to the campus. So some of the equipment, the solar Taurus 70 is pictured here on the left. And then on the right, again, you see this Taurus 70 at the top of that image. Somewhat unique design, which is why I wanted to show the photo, but I call it the horseshoe. So the CT's at the top of the photo, and you see the ductwork kind of wrap around to the bottom of the photo where you see the HRSG. So because of space constraints, couldn't do a linear lineup or even a 90-degree lineup. It ultimately ended up as a kind of a U-shaped lineup of equipment. They also added the fuel gas compressors. These are 100% each, so fully redundant fuel gas compressors. The Taurus 70's gas pressure requirements was more than what could be provided by the utility, so they added the gas compressors. And then also a new air compressor and inlet air filter and lube oil cooler. From an aerial view, we can kind of see on the left, it's pre-upgrade. You kind of see the 4 stacks sticking out of the top. That's 3 boilers. The bottom 3 are boilers, and the top is the older CHP. And then the photo to the right, you can kind of see one of those stacks went away. They still maintain boiler 1 and 2, but boiler 3 went away to make room for the new HRSG, and the top stack kind of stayed the same, very similar for the new CHP. Kind of gives us an idea of layout inside the building. So at the top of the image, we see the whole previous lineup. The CT kind of faded back in the line work there. CT and HRSG. The new CT was large enough it almost took up that whole space. And then at the bottom of the image, boiler 3 was removed and the new HRSG was kind of put in its place. So if we're tracking through this image, the hot gas out the far left of the page, and then as it comes up and down is where the stack is through the HRSG, and then that angled duct working back to kind of the center of the page there. So pretty unique arrangement. Probably won't see many arrangements like that, I would guess. From a elevation view, on the left we see the design drawing showing the removal of the panels and the glass, and then on the right you can kind of see where that sits in the building. Doesn't give you a good feel of really how tight and congested the space is, but we're looking at that bypass exhaust stack and CT, if we could look into the page on the right there. So I talked about the different equipment. You kind of think about replacing a CT and HRSG with a previous CT and HRSG, and it's some of the same equipment. It doesn't seem like maybe there would be a whole lot of changes, but there's quite a few changes for this project. You know, upgrading the 60 to the 70 Taurus, new switch gear you can see on the right there. On the left, cabling and duct banks. Far right bottom there is the pad for the Black Star generator. It's kind of a lot of things going on just to swap out a CHP. And then piping is on the top left there. We're looking at the fuel gas into the compressors. On the right is the duct burner gas train, and then just some various different piping changes throughout the plant. This was a cool video. I checked the audio. I didn't get it, so I'm not going to play it. If anybody wants to see it, it's a video that kind of talks about the owner. The owner's in the video, president of EMU, Engie's in it. They talk about how this whole project came together and the excitement around the campus and the savings that they're going to expect to see. And it's just a very positive video that goes through the benefits from their perspective. I had about 10 or 15 seconds, but I'm not. So I'd like to share that with folks if I could. Just get my email and send me an email, and I'll send you a link. Oh, this was it, but okay. So overall, results, it's been in operation for about 15 months. Everything's going very well. Guaranteed savings have been met about 40 to 50,000 a week as expected. And then some of our key takeaways. About a $20 million project. Replaced that aging unit. Reduced CO2 and net annual savings of about 2.8 million. Okay, that's it. Questions? Yes. Yep, that's a good point. They did operate it. That's always a place where somebody, when they're putting in CHP, they look at the boom or other options. EMU had a CT already, so the operators felt pretty comfortable with that. The integration of the Black Start was a little tricky. I didn't go into a lot of detail, but because the load profiles are so different, they're using their duct burners a lot. There's definitely components to this arrangement that add some challenges to their operators, but because they had a CHP before, they decided to go ahead with that model. Okay, thank you.
So next we have Bill Castor. He is the Director of Business Development for Power Systems with Siemens Energy. Hails out of Denver, Colorado. And his presentation is titled Navigating Through the Challenges of Implementing Successful On-Site Generation Solutions in a Complex Market. So help me welcome Bill Castor.
Hi. So I originally, I guess I thought when we did this, and as you can imagine, we had really a lot of latitude in what we wanted to speak about here today, but it was really focused on the future of CHP. So I had thought that maybe talking about the commercial aspect of it, what makes them successful, what the fundamentals look like, would be a good precursor to the conversations, the presentations that my colleagues gave. I think they touched a lot of the bases that I think are important here. So I think it's actually probably better doing this in the opposite way of what I thought, which is kind of standard for a married man, I guess. So are there any developers in the room? I kind of think I'm talking mostly to engineering folks, and other than you. So I was a developer for small power systems, CHP systems, for many years before joining Siemens. I still see myself as a developer role, but these systems that you've seen examples of being successful are probably 1 in 8, 1 in 10 kind of ballpark. They die from 1,000 cuts many times before they are successful projects with decisions to be made about the details around engineering and coordination, that sort of thing. So I guess with with that said, my intent is to talk more about those fundamentals and what, I think, helps the future of CHP, both for utilities, utility owners, or for consumers who might be the hosts, like we've been referencing earlier. And so, again, the CHP diagram, I think everyone here understands the fundamentals of that, the efficiencies that come from that, so I won't bore you with that. But I think when you are looking for opportunities for CHP development, it's important to remember that there are some key pieces of the puzzle that you can't just go around. They're things that require a great deal of expertise and some luck frequently, frankly. The thermal energy requirements that we've talked about with these other projects is obviously a key. The site and the space, again, whether you're doing a new one or converting someone from, that has boilers today and takes their electricity from the grid, a suitable site is, it sounds easy and small. Frequently, it's not the case at all. Reliable fuel supply and the right kind of fuel is always a component of that. And one thing that's becoming, I was going to say increasingly, but I'm tempted to say that maybe it's actually easing in its pressure. I think historically throughout my career, you are frequently at odds with the IOUs, the investor-owned utilities. Today, I think that's changing a little bit, and one of the things that I reference in here is I think that one of the keys is working alongside the utility, or some of the more forward-thinking utilities, frankly, are seeing ownership of the CHP and operation of CHPs as something they want to get into and have the expertise to do. So before we start talking about the future of CHP, I always think it's somewhat beneficial to talk about where we are. And you probably read these things a lot, but I think in the big picture, there are a few things that drive CHP that probably are worth considering. After following GDP growth since the 1950s, the demand for electricity, frankly, has been flat since the early 2000s and remains so today. So utilities are not seeing big load growth as a way, a logic for building new generation facilities. On top of that, you see, various fuels, including natural gas, either in the spot, as shown in the lower left, or even the forwards. They're relatively cheap, and everybody believes they're going to remain at that level going forward. With rare exception, electricity prices are low, and the Northern and Southern California peak prices, one exception to that, but even with that, relatively low prices. So I think to summarize, demand is flat, and energy is pretty cheap these days. So that is difficult standing alone as something to motivate someone to consider CHP alternatives. This, I think, certainly if you've seen anything I've done in the past, but probably different varieties of this. The traditional grid was one direction, right? Large generation going to customers down the line. Today, that's changed and it's evolved for multiple reasons, but it's much more of a distributed system today. And I think the drivers for that are again somewhat obvious, but it's created an environment where we've taken an old template, an old grid, not designed to do this, and really forced utilities to start looking at how they can manage that old template, that old system into incorporating all of these new intermittent, non-dispatchable resources that are no longer in one place, but they're distributed everywhere. But I think the I guess summary for me on this is that I think what this leads me to believe going forward is that renewables are going to continue to proliferate. Natural gas combined cycle will probably be the prevalent dispatchable resource that helps make those work. So that again plays into the future development for the CHP business. This is, I guess, in deference to my utility friends. I think if you look historically, the demand side hasn't changed a heck of a lot. What was easier for the old system, the grid was much easier to maintain when there wasn't as much renewable penetration, and when they had a lot more dispatchable resources to be able to manage that with. Going forward to the modern grid, you see wind, which frequently peaks when the demand isn't there. Solar, which peaks in the middle of the day again when demand tends to be soft. But what the utilities are being asked to do is to manage these things and balance those things with a lot of resources that they can't control. They're kind of takers for the wind and the solar, and so the way to manage that, frankly, has been a lot of investment in the grid. So when I'm talking to consumers and potential customers for CHP, frequently I find myself trying to explain that just because energy is cheap, as I described a couple of slides ago, doesn't mean that your cost of electricity is going to be cheap, and it doesn't impact your steam side of the business at all. So I truly believe that the cheap energy side but the significant investment that's happening, and I think is projected to happen on the grid, is going to impact you as a consumer if you're taking electricity from that grid. So don't get tricked into thinking cheap energy means cheap electricity, I guess is the message there. Again, the real key to this, and in every case you talk about with CHP, is the thermal side that is most important. So I did just a couple of things there because I don't think it's easy for people from the power business to think about electricity as the primary thing. When you're looking at CHP, frequently you're talking about boilers and steam as the primary driver, either for efficiency reasons or reliable supply, or again, it's a big component of their costs. So the steam piece is important, and we do have a lot of steam-intensive industries remaining in the U.S., so they represent, I think, a big portion of the opportunity. A lot of those candidates, and this is, either you as a consumer that might be in these, or if you're looking for CHP opportunities, I think chemicals, paper, and the food industries are the obvious places where a lot of thermal energy is critical to their processes. So that's where a lot of that is coming from. And I think for all of these cases now, it's natural gas has been and continues to be the fuel of choice. What I think is compelling here is and bodes well for the future of CHP is that 75%, is actually a little bit more than that, of these boilers are well past what their initial useful life was expected to be. So 40, 50-year boilers is not at all uncommon, and a lot of these are in the industries which consider their thermal energy supply, their steam, to be critical to their reliability and their competitiveness. So as I said, I think the almost adversarial relationship between utilities and consumers when it comes to CHP implementation has softened a bit. Some of the more forward-thinking utilities, either because they've become enlightened as a way, they think this is an opportunity for them, where large power projects are no longer have as much opportunities, but a lot of the IOUs are now required to look at their CHP opportunities and the potential on their system as part of their IRP process. So I think that has driven some of them. On the consumer side, it's a cost equation, as these folks before me talked about, but it's not just electricity. Again, the efficiency and the reliability of their steam supply is critical to consumers. So that's part of it that doesn't necessarily pop up for an IOU that might be considering this. Operating flexibility for the IOU, I think that means, as we had discussed before, the potential not always there, doesn't always make sense, but the utility ownership side could choose to oversize it and export some power from a location like this and help to bolster the grid and support it in a weak part of their system. Consumers see the flexibility more as potentially having other fuels when they have it on site, or being able to operate it not to try to avoid the peak power prices that are kind of given to them and be a market taker, if you will, but to have a system that is beholden to their operation as opposed to the other way around. So I'll try to move through these a little bit more quickly, but the reliability and resiliency, again, I think that's an obvious one for the utility and the transmission system. But on the consumer side, reliability is not just an electricity story, and it's frequently a steam side of the story. Again, for the utility, they can avoid the potential cost of transmission lines by adding generation in remote locations or weaker parts of the system, and the consumers avoid their exposure to that cost increase by bearing the cost of the investment that the utilities are making in the grid to serve them. Environmental regulations, again, I think that's just the design of the system. The investment tax credit is a major driver, especially for some of the consumers, but for utilities as well. They can benefit from that. And then consumers, I think, have the business model that Doug spoke to earlier. When they want to focus in a competitive market, put their capital into their manufacturing systems or their infrastructure and focus on their core business, this third-party deboom kind of concept, that type of business model, not only gets you an expert who's done this before, but also gets, potentially they use their capital, you can pay for it over time. So I think that helps the consumers for this. And really, the uncertainty. And for me, I don't profess to know what's going to happen in this market. I've seen some of my presentations from 15 years ago, and they're totally wrong about gas prices and all of that stuff. So for me, CHP is a way to manage that uncertainty. If you admit you don't know what's going to happen, I think for me there's a tendency to want to take control of my own destiny instead of just be there to take whatever someone else decides on the pricing standpoint and the utility standpoint. For utilities, it's a little bit different. I think it's much clearer for utilities these days. Your largest customers, if they require steam or thermal energy of any kind for their process, and their competitors are doing it. If you don't do it to help them be competitive and reliable, someone else will be there to do it. Some key trends, and again, I'll move kind of quickly, but utility ownership I had mentioned, that's becoming much more common these days. Natural gas for the new systems being built this is like fresh off the presses from last year. 72% of them were natural gas fueled, and the biomass and biogas systems were a minority of that. But that plays into the next one in this chart. You can see that while there have been, the size of these things has been kind of on a pretty normal trend for several decades. Over the last handful of years, as the industrial basis for these things has become a little bit not as fruitful for the hunting, a lot of these systems have moved to the smaller kind of systems with recip engines for hospitals, universities, that sort of thing. So the size of each installation has gotten significantly smaller over the time I've been in this business, and I think that appears to be continuing. And then I think the graph shows that this is again just the potential for CHP systems. It's really not an analysis of whether it makes any kind of financial or economic sense, but a majority of the capacity, not the number of projects, but the size of the projects, still remains in those chemicals, pulp and paper, and those businesses that I spoke to earlier. So a lot of those systems, as I mentioned earlier, are 40, 50 years old. So there are opportunities not just for new ones, but for replacement or investment in the existing ones. This is a little bit of an advertisement, but I think it's in deference, I guess, to what Doug and Jack had said. I think many of these consumers, especially, are doing this for the first time and may only do it once in their career. Many utilities have done large power plants, have never done small power plants. For me, the lesson is the same for these folks. It's really, I think, critical that you find partners that can help you evaluate where you are, what alternatives you have, and recommend a solution that is best for you, not necessarily someone who is selling a thing that they're looking for a home for. So I think the more complex the market on the outside gets, the more aware of that situation and the more expertise you need from an advisor or a partner when you're looking at implementing these things. Thank you. How'd I do? Any questions? Yes. Yeah, I don't know. I think there's always been a constant drumbeat to some degree. I think it's about the third time in my career when gas gets cheap, everybody has these projections of how it's going to take off and it's going to blast off. I think some of it is probably due to the large industry in the States have not always been a booming business, right? I think we've dialed back some of those things, and having cheap natural gas helps, but we're still not necessarily the economy in the world where if you were going to build a new chemical plant historically, I say up until maybe the last handful of years, it probably wouldn't have been built here, on the Gulf Coast as a first option. So I think some of those things happened a long time ago, moved offshore, went different places for various reasons. So I think the large ones, went away, but I still think there are a handful of places talking about them. They've gotten much smaller and don't make as big of a splash. Again, I think the systems are getting a lot smaller, and commercial buildings and that sort of thing aren't necessarily our stomping grounds all the time. Yes. On the CHP side, just honestly, I've seen and heard about a few from studies. I've not been involved or seen any of them, but again, it's not. I'm not necessarily going to apartment complexes trying to look at KW size systems, and I think that's I think large companies for sure, Siemens and people in our business, but also large engineering firms are being forced to look at new parts of the business that they haven't before. And I think we're all kind of trying to adapt to those things getting smaller, and it's significantly smaller where the fuel cells are trying to be implemented. I haven't seen them, and honestly, so 25-ish kind of years now, and I've always thought fuel cells made a hell of a lot of sense, but you can never make the math work, right? I mean, I think especially I think the clean drivers will help them. I still haven't seen anyone really put forward a compelling case from a cost standpoint on a fuel cell. Yeah. So I'll take them in reverse order because I have a short attention span. So I think it's very common when you go to a potential customer that they already have boilers, obviously, and almost every case, some of those boilers will be left in standby operation or even supplementing. So you would undersize the steam production maybe a little bit out of the CHP, so you're always keeping one of those able to respond quickly if you have an interruption on the steam side. So rarely, I've never seen somebody add a boiler along with a CHP, but very commonly seen boilers that are there remain in an auxiliary or a supplemental kind of firing mode, so they have that to fall back, as a redundancy. I tell you, on the as I was talking, I forgot your other question. See, I told you I was short attention span. Oh, the black start. Yeah. Sorry, thank you for the reminder. So that's one of the reasons I think it's important to get some expertise to help you, because I think that is one of the things that is dramatically oversimplified when if you talk to someone that is not in the engineering side of the business, someone that in the food and beverage industry, for instance, they think that's an obvious benefit. They don't necessarily consider the complexities that go with a black start, and often I honestly see them operating the way that Jack described. They instead of totally disconnecting, they will go up to a point and keep a little bit of import electricity all the time, so that they're always in sync and able to respond quickly, as opposed to trying to island themselves. It can be done. There's just it's just time and money, right? But it tends to be one of those things that everyone thinks of at the beginning, oversimplifies, and as you get further into it, it's honestly, I would say about 1 out of maybe 5 end up actually trying to do that, and it's only in very critical kind of applications that I've seen. I guess just one man's view, but that's what I've seen.
We had a bonus paper added to today's session. We had to cancel another one, but this paper fit right into what we're talking about here today. And the gentleman that will be speaking is Mike Welsh. He's with Siemens. He's been in gas turbine technology for over 35 years. He hails from Lincoln in the UK, and he's business development for gas turbines with Siemens, and his favorite color is blue. So he's going to be speaking about enhancing the economic benefits of cogeneration through additional flexibility. Please help me welcome Mike Welsh.
Okay, hopefully this is going to work. As I said, I found myself homeless for this presentation, so thank you for staying along and thank you for allowing me to join the session. Slightly different focus, because I'm going to have a very different view, because I'm on the other side of the pond. And it's quite interesting listening to the conversations you've been having here today, because we've been having these for the last 5 years. You hear a lot about flexibility, decentralization, decarbonisation, and digitalisation about the power industry. You hear it at every conference. And CHP isn't immune from this. And we're certainly seeing a lot of these challenges hitting us now in Europe with market reforms, high renewables penetrations, etc. And the one thing that people are now starting to ask for more and more in Europe is actually decoupling of power and heat. They still want their CHP plants, but they want them to be flexible so they can match the electricity demand, match their heat demand, export power, import power as and when necessary, because of the way the market reforms have taken place. Well-known slide. As somebody mentioned, though, it's very difficult sometimes to convince an actual factory manager to put in CHP, because he's interested in his own plant and he wants to spend as little money as possible. So it's quite difficult. This was actually a case study from Algeria. Somebody was going to build a new paper mill, and his idea was, I was going to put in boilers and put in reciprocating engines for my own power plant, no CHP whatsoever. So we had to go along and persuade him that we could actually save $3.45 million US a year on your operating costs by putting in a CHP plant. That got his attention. Environmentally, he wasn't bothered. Now, of course, the ideal CHP case, you want everything to be nice and steady 24/7, 365 days a year, but it's never actually like that. That's from a Swedish paper mill. You can see power and gas demand and electricity demand is all over the place. But you also, if you're using a gas turbine CHP, you get the daily variation, because the gas turbine output varies over the course of the day. So you pick a design point, And sometimes you will be producing less power than that design point, sometimes more. So how do you use that surplus? How do you cope with the lack of power generation, like the continuous import from the grid? But you also have the same problem with steam. Sometimes you get all the steam you want, sometimes you don't. And people do put in supplementary boilers alongside their cogen plant at the same time. It gives them that standby capacity. Especially if you're a new build factory, they want that extra redundancy. And sometimes they'll replace their old oil-fired boilers with new gas-fired boilers at the same time. Now, one of the little tricks with the gas turbine is it doesn't use all the oxygen in the combustion process in the gas turbine, so the exhaust gases are oxygen-rich. So you can basically use an afterburner to boost your steam production, and that takes you from this blue line here, which is the variation of steam production with gas turbine load, up to this green line here, or if you want to, you can actually fire the boiler even more and keep constant steam production with variable electricity production. That enables you to undersize your gas turbine. So you don't need a 15 megawatt unit to produce exactly the amount of steam if your factory load is only 7 or 8 megawatts. And that gives you a lot of decoupling of heat and power very reasonably easily. And the other thing about supplementary firing is because your exhaust gases are already at 500 degrees C or thereabouts, you're not heating air in your boilers from ambient conditions up to the 750. You're already starting from a high temperature point, so your efficiency with supplementary firing adds an extra 2, 3, 4, 5 percentage points efficiency on your overall energy efficiency of the plant. Now, one of the things we found in Europe, though, is that your traditional heat match doesn't necessarily work, depending on the spark spread between your electricity price and your gas price. If you have high electricity prices, around about 5 to 6 times that of your fuel price on a dollars per kilowatt hour basis, you really should now try to tend your CHP plant more towards an electricity match than a heat match. And there we look at things like combi cogen with steam turbine with steam extraction, or a new concept that's hitting the streets in Europe is with organic Rankine cycle. Both of those give you slightly different heat to power ratios, but the mathematics, this is from a UK study that's ongoing at the moment. We looked at the traditional heat match and we looked at this combi cogen type match, and you can see you're saving somewhere just over £1 million a year on your operating costs by going through the combi cogen, simply because the electricity is so expensive. It's 5 times the cost of gas on a pounds per megawatt hour basis. And there's just a chart showing if you've got a little turbine, you can fire it to get a lot more steam than you would normally have. And looking at the sort of heat to power ratios, combi cogens around 1 to 1, traditional gas turbine CHP somewhere around 1.5 to 2 to 1, and your fired CHPs up to as much as 4 to 1 heat to power ratios. Now, the other thing is fuel flexibility can have a huge benefit as well. So while natural gas is the choice, fuel of choice worldwide, is there something I can get that's a lower cost? Is my natural gas supply guaranteed? In many countries in the world, industry gets cut off. Domestic consumers take priority if there's a gas shortage. So, can I actually get a cheaper gas tariff by having an interruptible tariff rather than a firm tariff? In which case, what can I use as a backup fuel? And having this fuel flexibility can offer you a lot of economic and environmental benefits, such as security of supply and a lower carbon footprint if you're flaring a process off gas, for example. Now, quick bit of maths. If I've got a 15 megawatt class gas turbine, then I can knock 50 cents per million BTU off my fuel bill. If I'm running for 8,000 hours a year, that's about $500,000 a year off my fuel bill, simply by fuel switching. And reality on a gas turbine, switching between fuels has very, very little impact on its performance. And we looked at a 25 megawatt class on LPG, which is one of the worst cases. You lose 2% on power output compared to natural gas, and 0.2% on the efficiency. An 8 megawatt class GT, that's actually at the University of New Hampshire, runs on processed landfill gas, natural gas, a blend of processed landfill gas or natural gas, and has diesel as a backup fuel. There's no impact on the power output whatsoever, switching between any of those gas fuels. There's lots of opportunity fuels out there, landfill gas, sewage gas. Process off gases are a big business now in Europe as people reduce flaring. High hydrogen gases from the petrochem industry in particular. coke oven gas. We have biogas units in China from the ethanol industry. Ethane is a wonderful opportunity fuel in some parts of the US because they can't do anything with it. It's a great fuel. And the backup fuels, diesel is the conventional backup fuel, but it's also really quite expensive and not very environmentally friendly. So people have looked at LNG, but that's actually quite a costly fuel to store. So why not look at other fuels like LPG and ethane again as your backup fuel? Much easier to store, much more environmentally friendly when you burn them. And you can burn them as a gas as well, so switching between natural gas and those as your backup fuels is automatic. CHP is being incorporated into many micro mini grids. In fact, in many places it's forming the heart of this grid system. And that now brings in the digitalization aspect. And if you have really good control systems and control software, you can now do real-time fuel switching, importing, exporting of electricity, deciding when to store energy, when to release it. And critically, what we're finding in Europe, it provides that local grid support potential, because the high renewable penetration in some countries, which had previously very good stable grids, we are now seeing 2 or 3 power cuts a week, disconnections a week in Germany of all places. And so we've had people with continuous processes now come to us asking, please can you put in a cogen scheme for us because we need the security of supply. We can't have our electricity shut off twice a week. It's costing us too much. So it's an opportunity there for the utilities to actually invest in a plant to help their customers. If you look at real-time pricing, you now have negative power in many countries, or low power prices during some parts of the day with wind and solar, and you have very high peak power prices. So with the right software, you can trade accordingly. And there are mechanisms in the UK and Germany, under the capacity mechanism, where the utilities will phone you up and say, please, can you take this surplus power? I will give it to you. I will pay you to take this power. And at other times, they'll phone you up saying, please, can you shut your process down? We need the power you can give us. And in some cases, the industry will make more money from selling that power for 2 or 3 hours to the utility than they will from making their product. So now you can look at incorporating energy storage technologies into your CHP system, batteries for storing electricity, to shift the peaks, reduce your peak demand tariffs, knock 1 megawatt off your peak demand tariff for a factory owner. That's a lot of money you're saving over a month or a quarter. Use it to trade in the export markets, or use it to create heat, store it as hot water, or in other systems like the electrothermal energy storage systems or heatcrete, to use as heat later on in the process to displace fuel usage in a boiler at some later time. And likewise, if you've got surplus heat, you can store it to use later when you've got a peak heat demand. Or there's a wonderful paper given at this conference last year by a Spanish company who actually used waste heat to create chilled water. And then during the peak hours of the day, when electricity prices were very high, they fed that chilled water to the inlet filter of the gas turbine, boosted its power output by about 25% because it's hot in Spain in the afternoon, and showed they had a 2-year payback by using surplus heat to create chilled water. So wrap up very, very quickly. There you go. You've got the environmental and economic benefits. There are many things you can do to make it flexible to suit the future markets that we're seeing and the need for flexibility that utilities and governments want. You can incorporate energy storage of all sorts. But above all, it does give your CHP user or your utility or your third-party operator the ability to generate additional revenue and capture those peak market times and those ancillary services payments, which make an awful lot of difference to a small scheme. And with that, thank you very much.